Built by the British company Short Brothers, the S.1 flying boat was constructed almost entirely out of metal, with the only exception being the fabric covering on the wings. By choosing duralumin as their primary material, the engineers made this aircraft truly unique. At the time, that kind of alloy was practically unheard of in aircraft manufacturing. Using it for the hull of a seaplane was a revolution in British aviation history. The engineers used this lightweight metal not just for a strong internal frame, but for the outer skin as well. Thanks to this bold approach, the S.1 became the first all-metal light seaplane created in Great Britain, and quite possibly the very first in the world. But the innovation did not stop there. Unlike typical light aircraft of the era, this model featured a twin-engine layout. This was something usually reserved for much larger, heavier aircraft. On top of that, the S.1 was a monoplane. This was another massive technical breakthrough for the time. Before we dive deeper into this all-metal flying boat, it is worth looking at the path the company took to actually build it. During World War I, Short Brothers was heavily involved in building rigid airships. That is where the company gained invaluable experience working with duralumin structures. Later on, at the 1920 Olympia Aero Show in London, the company introduced its new two-seat biplane. This was the Silver Streak. Powered by a Siddeley Puma engine, this aircraft was built almost entirely out of metal. This was mostly that same duralumin. The only exceptions were the wing spars made from steel tubing. Even the wing skin was made of duralumin. This used a clever method that Short Brothers engineers invented and patented. The fuselage had a clean, streamlined shape. But the real innovation was in the design itself. The aircraft featured a stressed skin construction. This meant the metal panels actually carried part of the structural load during flight. The shape of the aircraft was formed by internal frames. The metal skin was securely fastened to them using thousands of rivets. At the exhibition, the Silver Streak captivated both the public and aviation experts. They recognized it as a massive leap forward for the industry. In fact, it went down in history as the first all-metal aircraft designed and built in Britain. Over time, the concepts introduced in the Silver Streak evolved into a brand new model. This was the Short Springbok. This aircraft retained many of the successful design features of its predecessor. However, some elements had to be heavily modified to meet the strict requirements set by the British Air Ministry. This was especially true for the wing structure. Short Brothers did some incredible pioneering work in the field of all-metal aircraft. Fortunately, its revolutionary achievements did not go unnoticed. The Air Ministry had been keeping a close eye on the progress of the company. They officially approved the construction of new aircraft. These new designs were based on the exact same advanced metal structures developed at the Short Brothers factory in Rochester. It became clear that duralumin aircraft would soon dominate aviation. They would be following the same successful path as steel construction. Thanks to its bold and innovative vision, Short Brothers earned well-deserved recognition. Ultimately, this tiny flying boat served as an excellent practical experiment. It clearly demonstrated the hidden potential of low-powered seaplanes, proving just how advantageous this unique design could be. The story behind this aircraft is fascinating, so let us take a look at exactly how it came to be. Years ago, a wealthy Australian named Lebbeus Hordern purchased a converted F-5 flying boat. He bought it from the legendary aircraft manufacturer Short Brothers. This luxurious aircraft was powered by two reliable Rolls-Royce Eagle engines. It featured a spacious cabin where passengers could travel in total comfort. The airplane performed beautifully, and it flew extensively in the skies over Australia. Eventually, Hordern became interested in light aircraft. He wanted a compact seaplane, specifically a small flying boat for private leisure flights. Reaching out to Short Brothers, he asked if they could design a custom twin-engine aircraft just for him. Company head Oswald Short telegraphed back to accept. After hashing out the details, the engineering team got to work on the design and construction. And that is exactly how this unique aircraft was born. This partnership did not come together purely by chance. Oswald Short had actually been mulling over the idea of building seaplane hulls from metal since around 1921. Traditional wooden hulls always soaked up water over time, and they held up especially poorly in hot, humid climates. To turn this idea into something real, Short pulled together a small team of specialists. Among them was an engineer named C.P.T. Liscombe, who brought deep hands-on experience with duralumin. Together, they spent time studying how metal hulls would behave on the water and how well they would resist corrosion, patiently waiting for the right project to put their research into practice. Horton's request for a light seaplane suited to fishing trips around Sydney's Botany Bay turned out to be exactly the opportunity they had been waiting for. The resulting aircraft also earned a distinction all its own within the company. It became the very first Short Brothers design to receive an official design index number, S1, a numbering system the company would go on to use for decades afterward. At the time it was built, contemporary aviation reports also described it as the smallest flying boat ever constructed. This light flying boat from Short Brothers was a classic monoplane. It featured a very thin wing mounted to the fuselage using an elegant wire bracing system. Directly on the wing, engineers mounted two Blackburn engines. These were the exact same motors that had performed incredibly well a year earlier. They had proved themselves at the famous Lympne light aircraft trials. This was a well-known competition held in Kent that challenged designers to build ultralight aircraft powered by the smallest and most economical engines possible. The specific engines chosen for the Cockle were Blackburn Tomtits, a V-twin design of just under 700 cubic centimeters in displacement, small enough that they would not have looked out of place strapped to a motorcycle of the period. To reduce drag, an aerodynamic teardrop fairing was placed behind each engine. Interestingly, the Blackburn engines were not the original plan. The design team had first intended to fit a pair of Bristol Cherub flat twin engines instead. Those engines could deliver a respectable amount of power, but their vibration at full throttle proved troublesome for such a lightweight, delicate airframe. So the idea was quietly dropped in favor of the Blackburns. The replacement engines were also ungeared, meaning the propellers spun at the exact same speed as the engines themselves, capped at a modest maximum. That restriction limited just how much power the little seaplane actually had on tap, and it goes a long way toward explaining why simply getting off the water would later prove to be such a stubborn challenge. Because the motors were mounted deep within the wing structure, the designers had to use extended drive shafts. This allowed them to push the tractor propellers far forward. They reached right up to the leading edge of the wing. It is worth noting that these were direct drive shafts without any heavy reduction gearing. This meant the propellers turned at engine speed. It is fascinating to compare this power plant layout to another well-known aircraft of the era. That aircraft is the small Dornier Libelle flying boat. While both of these aircraft were built entirely out of lightweight duralumin, that is essentially where the similarities end. Their underlying design philosophies were fundamentally different. For example, the center section of the Dornier wing housed a single small Siemens radial engine. This engine drove a tractor propeller. To provide clearance for the prop blades and keep the thrust line balanced, the wing had to be mounted high above the hull. As a result, the passenger sat directly underneath the wing. In contrast, the British aircraft from Short Brothers took a completely different approach. Its wing rested directly on the hull. The two engines were mounted right on top of it. Because of this, the centers of thrust and drag were located much lower than on its German competitor. The distance between the propeller hubs was roughly 6 feet. This clever layout meant that if an engine suddenly failed, the aircraft would not yaw uncontrollably. The pilot could easily compensate for the asymmetric thrust using standard rudder inputs. Of course, flying on a single engine severely limited performance. Because of this, the aircraft could likely only maintain level flight without the ability to climb. Continuing the comparison, there was a striking difference in how these aircraft sat on the water. For lateral stability, the Dornier featured short sponsons extending from the lower hull. The engineers at Short, on the other hand, opted for traditional outrigger floats. These floats were suspended under the wings. The hull shapes were completely different as well. The hull of the Dornier was fairly boxy. Meanwhile, the Short flying boat featured beautifully curved forward sections. These sections smoothly transitioned into a rounded shape toward the tail. This comparison gets even more interesting when you look at their efficiency. The German flying boat was powered by a 55 horsepower engine. It could easily carry 2 people. Meanwhile, the 2 Blackburn engines on the British aircraft put out a combined total of around 40 horsepower. They could only get a single pilot airborne. Ultimately, both of these airplanes demonstrated an incredibly economical approach to flying, but they achieved it through completely different engineering philosophies. The hull of this light flying boat built by Short Brothers was very similar to the one first used on the Silver Streak. The core of the structure consisted of sturdy duralumin ring formers. The outer skin panels were riveted directly to them. The longitudinal stringers did not run straight through these frames. Instead, they acted as spacers to add extra rigidity between them. Up front, the shape of the hull smoothly transitioned into a dedicated planing bottom. This was essential for skimming across the water. Interestingly, this bottom section was built as a separate component and left open at the back. Because of this, any excess water would just drain right out as the aircraft climbed away. The planing bottom itself had a distinctive concave, V-shaped profile, and rather than just one step, it actually had two. The main step sat close to the aircraft's center of gravity, with a second, smaller one positioned roughly halfway back toward the tail. Both steps were built as separate fittings attached to the outside of the main monocoque shell, rather than being part of the load-bearing structure itself. This clever detail meant that even if a hard landing ever damaged a step, the main hull underneath would stay sealed and watertight. Looking inside, the entire structure relied solely on those formers. This made it surprisingly simple, but incredibly effective. It was exactly this brilliant simplicity and perfectly clean aerodynamic lines that became the hallmarks of this bold design. In the areas where the wings and tail section attached to the fuselage, the engineers used heavier, reinforced frames. However, even these reinforcements did not take away from the overall elegance and simplicity of the design. The interior space of the hull remained completely open. The structural elements only stuck out about 2 inches inward from the skin, if that. There were simply no unnecessary parts or complex internal cross-bracing. The cockpit was positioned right in the very nose of the seaplane. This gave the pilot an absolutely phenomenal forward field of view. Aside from the standard flight controls and levers, the cockpit featured an interesting detail. 2 dedicated starter levers, one for each engine. They worked essentially like a pull start on a lawnmower, letting the pilot crank the engines by hand. During factory bench testing, this system performed exceptionally well. It let you turn over those Blackburn engines with barely any effort. Thanks to this setup, the pilot of this light-flying boat could start the engines entirely unassisted. Out on long flights or during unscheduled stops on the water, that kind of self-reliance was absolutely priceless. The reliability of the hull itself deserves special attention. Long before the wings, engines, or even the cockpit were fitted, Short Brothers wanted to check on the single most important part of the entire design. Back in April 1924, the bare hull alone was floated on the water for a full day as an early trial, well before the rest of the aircraft was complete. It passed the test comfortably, giving the engineers real confidence to press ahead with the rest of the build. Once construction was finished, the aircraft was loaded with about 800 pounds of ballast. It was then left on the water for exactly 24 hours. The results were impressive. Over those 24 hours, the amount of water that seeped inside would barely fill a shot glass. This proved that achieving complete watertightness in metal hulls was entirely possible. This was true even though Short Brothers strictly refused to use any fabric tape to seal the seams. This was unlike the methods used on Dornier aircraft, for example. Of course, engineers still needed to see how a hull like this would hold up after long-term use. They also needed to test it through a series of hard landings on the water. But all signs pointed to the duralumin hull being at least as durable as a traditional wooden one. Plus, metal had one major advantage. It did not absorb moisture. According to engineering estimates, a large wooden flying boat could soak up as much as 600 pounds of water. This added a significant amount of dead weight. Since seaplanes spent most of their lives right there on the water, hull swelling and the resulting weight penalty were critical concerns. This is exactly why all metal construction became a true breakthrough in the future of aviation. The wings of this light-flying boat also featured a metal framework. They were built around corrugated spars and box-type ribs. They featured stamped lightning holes to keep the weight to an absolute minimum. The outer wing skin, however, stuck to tradition. It was covered in standard aircraft fabric. The 2 wing halves were securely bolted to the upper hull using heavy-duty steel bolts. They were reinforced by a pair of lift struts on each side for extra rigidity. The ailerons were absolutely massive. They ran the entire span of the wing and had an exceptionally wide chord. Flight controls relied on a clever system of bell cranks hidden inside the ailerons. These linked to push rods dropping vertically straight into the hull. These oversized ailerons actually did double duty. Both of them could be drooped downward together, working much like flaps to help slow the little seaplane during its landing approach. Out near the wingtips, the stabilizing floats that kept the aircraft balanced on the water were tucked inside streamlined, spat-like fairings. These helped cut down on drag while still doing their job of keeping the wingtips clear of the water. The empennage followed a completely conventional layout for the era. Its internal framework was built from tubular metal spars and box ribs. Just like the wings, it was neatly covered in lightweight aircraft fabric. To make the aircraft easier to handle on shore, the designers included a pair of large-diameter beaching wheels. These attached to an axle that slipped easily into a transverse tube. This tube ran straight through the hull, just above the waterline. Thanks to this simple but effective setup, a single person could easily move the flying boat around on the ground. Of course, this detachable beaching gear was not used in flight. The wheels were either left on the beach before takeoff or stowed inside the hull. This was done just in case the pilot needed to haul the aircraft out of the water at their destination. The naming of this aircraft also has an interesting backstory. Initially named the Stellite, the S1 ran into an immediate branding problem. The name was simply too easy to confuse with Short Brothers' other design, the S4 Satellite. To avoid confusion, they decided to change the name of the flying boat to the S.1 Cockle. It is worth pointing out that only a single prototype of the Cockle was ever built. It took to the skies for its maiden flight on November 7, 1924. However, the flight test results were disappointing. The flying boat exhibited mediocre performance and handling. As a result, the customer was completely unimpressed and refused to buy it. Getting the Cockle into the air in the first place had already been its own ordeal. Water trials began back in September 1924, but for weeks the little flying boat simply refused to break free of the surface. Engineers eventually increased the angle at which the wing met the airflow to help squeeze out a bit more lift. On the day it finally did fly, the test pilot even dressed as lightly as possible, shedding every spare ounce he could to lighten the load. Some at Short Brothers later joked that the Cockle only managed to get airborne that day because the atmospheric pressure happened to be unusually high, giving the thin, low-powered wing just enough extra lift to work with. The designers tried to salvage the project with a few minor modifications. Most of these changes focused on the tail. The original fin and rudder had been fairly small and triangular in shape. Engineers replaced them with a larger, curved, and more pointed design that more than doubled the surface area, giving the pilot much better directional control if one of the two engines ever cut out mid-flight. In January 1925, the updated S1 was leased to a British Naval Aviation Experimental Center at Felixstowe. But the aircraft was never destined for a long flying career. From then on, this unique seaplane never flew any major missions. Instead, it simply served as a testbed for routine material corrosion testing. Even so, the story of the little flying boat did not end there right away. In March 1925, engineers made an attempt to secure an official certificate of airworthiness for the aircraft, but the effort was unsuccessful. That July, the S1 formally went on loan to the Air Ministry at Felixstowe, where it was assigned the military serial N193. Coaxing it into the air remained difficult, but that September, Short Brothers' own chief test pilot, John Lancaster Parker, gave a demonstration flight that showed off what the little seaplane could do. Despite its underwhelming performance, the aircraft still managed to impress observers, largely thanks to just how well its metal hull was standing up to corrosion after months of exposure on the water. The following year brought one more chapter to the story. In August 1926, the Cockle was brought back to the Short Brothers factory and fitted with a pair of geared-down Bristol Cherub engines, the very type that had originally been considered before vibration problems ruled them out. With this new power plant, it flew several times during June and July of that year. The Air Ministry then purchased the aircraft outright and sent it back to Felixstowe, where it flew at least once more, again with John Parker at the controls, before settling into its long-term role as a corrosion test subject. Later still, fitted with even more powerful Cherub 2 engines, the little seaplane managed one further flight in June 1927, reaching a top speed of roughly 73 miles per hour. Its very last flight took place in early October of that same year. Although the S.1 Cockle never became the comfortable passenger seaplane that Lebbeus Hordern had originally envisioned, it left Short Brothers with something arguably more valuable: hard-won, practical experience in building watertight, corrosion-resistant metal hulls. That knowledge did not go to waste. At almost the same time the Cockle was under construction, Short Brothers had also begun work on a much larger metal hull, intended as a replacement for the wooden hull of a Felixstowe F5 flying boat. This became the Short S2. Because the smaller Cockle hull was simpler, it moved through development faster, and the lessons learned from solving its problems were fed directly into the S2 program. From there, that same body of knowledge went on to shape two of Short Brothers' most successful flying boats of the era, the Short Singapore of 1926 and the Short Calcutta of 1928. For all its modest size, the finished S.1 Cockle was a genuinely tiny aircraft. It measured just under 25 feet in length, with a wingspan of about 36 feet and a wing area of roughly 210 square feet. Empty, it weighed only around 880 pounds, rising to a gross weight of about 1,200 pounds when ready to fly. It was a remarkably small package to carry such an outsized share of aviation history. It is worth remembering just why corrosion testing mattered so much to Short Brothers at the time. Duralumin, the alloy at the heart of this entire story, was prized for combining the strength of steel with a fraction of the weight, but it also had a well-known weakness. Early formulations of the material could be vulnerable to corrosion when exposed to salt water over long periods, a serious concern for any aircraft meant to spend its working life on the sea. By quietly monitoring how the Cockle's hull held up year after year at Felixstowe, engineers were able to gather exactly the kind of long-term, real-world data that no short trial or laboratory test could ever fully replicate. In that sense, even after its flying days were essentially over, the little seaplane kept right on doing useful work for the company that built it, feeding lessons into every metal-hulled flying boat that followed it down the slipway at Rochester.